Let me ask you something. What time is it? No, I do not mean look at your watch. I mean, what time is it for you right now compared to me? You probably think that is a silly question. You would say, well, it is the same time for both of us. We are sitting in the same room. And that answer feels so obvious, so clearly right, that you have probably never questioned it. Not once in your whole life, but I am telling you it is wrong. Right now, at this very moment, the clock on your wrist and the clock on mine are ticking at different rates. The difference is tiny, fantastically small, but it is real. It is not a trick, not a thought experiment, not something that only matters inside an equation. It is a measured, confirmed physical fact. And once you understand why, you will realize something that most people never grasp. Time travel is not science fiction, it is science. It is happening to you, to me, to every object in this universe. It has been happening since the beginning of everything. So let us start with something very simple. A clock. What is a clock, really? Strip away the gears, the springs, the digital displays. A clock is anything that does the same thing over and over again, in a regular way. A pendulum swinging back and forth, a quartz crystal vibrating 32,768 times per second, an atom jumping between two energy levels with extraordinary precision. The point is not the mechanism, the point is repetition. Tick, tick, tick. Each tick marks off a unit of time. That is all a clock is. Anything that counts a repeating process. Now, if I have two identical clocks sitting right next to each other on this table, they tick at the same rate. Obviously, you test them, you compare them, they agree. Tick for tick. Good. We feel comfortable. We feel like we understand time. It flows at a steady rate, the same everywhere. And clocks just measure that flow like buckets catching rain. Isaac Newton felt exactly this way. He wrote about it explicitly in his Principia. He called it absolute time. True and mathematical time, which of itself and from its own nature flows equally, without relation to anything external. A great cosmic river carrying everything forward at the same speed. It was a beautiful idea, and for 200 years nobody had any reason to doubt it. Newton built mechanics on top of it, engineers built bridges with it. It worked perfectly because at the speeds and scales of ordinary human life, it is essentially correct. But it is not correct. Not exactly. And not exactly turned out to be one of the most important phrases in the history of physics. What happens if I pick one of those clocks up and start moving it? This is where your intuition is going to start getting into trouble. And I love when intuition gets into trouble because that is exactly where you learn something new. Nature is under no obligation to make sense to you the first time you look at it. See, there was a fellow named Albert Einstein, and in 1905, working as a patent clerk in Bern, Switzerland, 26 years old, no laboratory, no research group, just a desk and a brain. He published a paper that shattered Newton's absolute time into pieces. And the strange thing is he did not start with time at all. He started with light. Einstein asked a deceptively simple question. One of those questions a child might ask that makes a professor sweat. What if the speed of light is the same for everyone? Not just for someone standing still, but for someone running. Someone in a car, someone on a rocket going half the speed of light already. No matter how fast you are moving, no matter which direction, if you measure the speed of a beam of light, you always get the same number, about 186,000 miles per second, 300 million meters per second. Always. That is not negotiable. Nature insists on it. And by the way, this was not just a guess. There was experimental evidence. Two fellows named Michelson and Morley had tried very carefully back in 1887 to detect differences in the speed of light depending on the direction of measurement. The logic was sensible. The Earth is moving through space at about 67,000 miles per hour as it orbits the Sun. So if you shoot a beam of light in the direction of the Earth's motion, it ought to be slightly faster relative to you than a beam going sideways. Just like swimming downstream is faster than swimming across a river. They built an exquisitely sensitive instrument called an interferometer, capable of detecting speed differences far smaller than what they expected to find. They ran the experiment, and they found nothing. Zero difference. The speed of light was stubbornly, defiantly, maddeningly the same in every direction, no matter how the Earth was moving. At the time, this was considered a failure, a null result. People scratched their heads and moved on. Einstein looked at the same result and saw it not as a failure, but as a clue. Perhaps the speed of light is not behaving strangely. Perhaps our assumptions about space and time are what is wrong. At first, the constancy of light speed sounds harmless. Fine, light has a fixed speed, so what? But think about what that really means. I want you to think about this carefully because everything follows from this one idea. If you and I are moving relative to each other, and we both measure the same beam of light and we both get the same speed, then something else has to give. The arithmetic does not work if time flows at the same rate for both of us. Something has to be different between us to make that result come out right. And the thing that gives, the thing that bends and stretches and adjusts to preserve the constancy of light, is time itself. Let me paint you a picture. Imagine a very simple clock. Two mirrors, one on top of the other with a gap between them and a single pulse of light bouncing up and down. Every time the light hits the bottom mirror, that is one tick. Up, down, tick. Up, down, tick. Simple. Beautiful. The purest clock you could ever build because it runs on light itself and we know exactly how fast light goes. No gears to wear out, no battery to die, just photons and mirrors. Now put that clock on a train moving past you at tremendous speed. You are standing on the platform watching. What do you see? From your point of view, the light pulse is not just going straight up and down anymore. It cannot be because while the light is traveling upward, the train has moved sideways, so the light goes up and to the right, then it bounces off the top mirror and comes back down, but the train is kept moving, so it goes down and to the right. The path is a zigzag, a diagonal up, then a diagonal down. A diagonal path is longer than a straight vertical path. So that is just geometry. Pythagoras, the kind of thing you learned when you were 12. But the speed of light has not changed. We said it cannot change. That is our starting point, our bedrock, our one non-negotiable fact. So if the path is longer and the speed is the same, the time to complete each trip must be longer. Each tick takes longer. The ticks of that clock, from your perspective on the platform, are farther apart. The clock on the train is running slow. Not because it is broken, not because it is a bad clock, not because the heat from the engine is somehow affecting the mirrors. It is running slow because time itself for that moving system is genuinely passing at a different rate than it is for you. And it is not just the light clock. Every clock on the train is running slow. A pendulum clock, a digital watch, a beating heart, a chemical reaction, a birthday candle burning down. Every process that unfolds in time slows down by exactly the same factor. Because it is not the clocks that are affected, it is time. This is called time dilation. And I need you to resist the urge to explain it away. People always want to say, well, it is not really time that is slowing down, it is just some mechanical effect on the clock. No, it is everything. It is all of reality aboard that train. The passage of time itself is altered by motion. How much slower? There is a formula, and it is elegant. The time dilation factor depends on the ratio of your speed to the speed of light, and it involves a square root. At everyday speeds, the effect is absurdly small. A car going 60 miles per hour experiences time dilation of about 1 part in 10 to the 15th power. That is roughly 1 second difference over 30 million years. Unmeasurable in daily life. But it is not zero. And as you go faster, the effect grows. And it grows not in a gentle linear way, but savagely. The closer you get to the speed of light, the more dramatically time stretches. In 1971, two physicists named Joseph Hafele and Richard Keating did one of the most satisfying experiments in all of physics. They bought airline tickets, regular commercial airline tickets on Pan Am and TWA. They carried 4 cesium atomic clocks onto the planes, strapped into their own seats like tiny rectangular passengers. They flew east around the world on one trip, west around the world on another. Then they brought those clocks home and compared them to identical clocks that had stayed put at the United States Naval Observatory in Washington. The clocks disagreed. The ones that flew eastward lost about 59 nanoseconds compared to the ground clocks. The ones that flew westward gained about 273 nanoseconds. Billionths of a second. Tiny, yes, but measured, real, and exactly, precisely, beautifully consistent with what Einstein had predicted more than 60 years earlier. The moving clocks ran at different rates. Time passed differently for the clocks that traveled, a few hundred nanoseconds. You might be tempted to shrug. Who cares about billionths of a second? It does not affect my life. Hold that thought, because we are going to come back to it, and when we do, you will see that it affects your life every single day. But first, I need to add another layer, because Einstein was not finished. Not even close. 10 years after special relativity, in 1915, he published the general theory of relativity. And in this one, he showed something even more unsettling. It is not just motion that affects time. Gravity does too. Think about this. You are standing at the bottom of a tall building. Your friend is standing on the roof. You each have identical clocks. Perfect, flawless atomic clocks. According to general relativity, the clock on the roof, farther from the center of the Earth, sitting in slightly weaker gravity, runs faster than the clock in the lobby. Not by much, but it runs faster. Gravity slows time down. The stronger the gravitational field you are sitting in, the slower your clock ticks compared to someone in weaker gravity. Why? Because gravity, Einstein realized, is not really a force pulling on things at all. That was Newton's picture, and it works beautifully for calculating orbits and trajectories, but it is not what is actually happening. What is actually happening is that mass and energy warp the geometry of space-time itself. The Earth does not reach out and grab you. The Earth bends the fabric of space and time around it, and you follow the curves in that fabric. Near a massive object, space-time is more curved, more distorted, more bent, and one consequence of that distortion, one you can measure with sufficiently precise clocks, is that time runs slower. Picture it this way. Imagine space-time as a rubber sheet, and the Earth is a bowling ball sitting on it, making a dip. Things near the bowling ball are in the deeper part of the dip, where the sheet is more stretched. Clocks in that deeper region tick slower. Clocks farther out, where the sheet is flatter, tick faster. It is not a perfect analogy, because space-time has 4 dimensions and a rubber sheet has 2, but it captures the essential idea. Curvature slows time. In 2010, physicists at the National Institute of Standards and Technology performed an extraordinary experiment. They used aluminum-ion clocks, the most precise timekeeping devices ever constructed, accurate to about 1 second in 3.7 billion years. They placed one clock just 33 centimeters, roughly a foot, above the other, 13 inches of height difference, and the higher clock ticked faster, by an amount so small it defies everyday imagination, about 4 parts in 10 to the 17th, but measurably, detectably, undeniably faster. 1 foot of altitude changed the flow of time. This means that your head, right now, sitting there in your chair, is aging faster than your feet. Over a lifetime of about 80 years, the accumulated difference between the top of your body and the bottom comes to roughly 90 billionths of a second. Your head is a time traveler compared to your feet. A very modest one, but a real one. And this is not just laboratory curiosity, this is engineering reality. Engineers who build the systems you depend on deal with relativistic time correction every single day. Consider the global positioning system. 24 satellites orbiting about 12,500 miles above the Earth, each carrying atomic clocks. Your phone calculates your position by measuring the tiny differences in when signals from different satellites arrive. The physics of relativity hits this system from both directions simultaneously. The satellites are up high in weaker gravity, so general relativity says their clocks gain about 45 microseconds per day compared to ground clocks. But the satellites are also moving fast, about 8,500 miles per hour. So special relativity says their clocks lose about 7 microseconds per day due to time dilation from speed. Put those two effects together. 45 microseconds gained minus 7 microseconds lost equals a net gain of about 38 microseconds per day. 38 millionths of a second. Sounds trivial, but light travels about 7 miles in 38 microseconds. If the GPS system did not correct for this, positioning errors would accumulate at roughly 6 miles per day. In 2 minutes, your position would be off by the length of a football field. After a week, you could not tell which city you were in. Every time you follow directions to a restaurant or navigate an unfamiliar road, you are relying on corrections for relativistic time dilation. You are depending on the fact that time is not absolute. You are, in a very practical sense, benefiting from our understanding of time travel. Let me push harder now, because so far, all these effects are tiny. Nanoseconds, microseconds, billionths of a lifetime. What happens when you really crank up the speed? At 10% of the speed of light, time dilation is still modest, about 0.5%, barely noticeable. At 50%, 1 year on the rocket corresponds to about 1 year and 2 months on Earth. The difference is starting to show. At 90% of light speed, every year you experience corresponds to roughly 2.3 years passing back on Earth. At 99%, 1 year for you means about 7 years pass at home. At 99.9%, it becomes more than 22 to 1. and at 99.99% of the speed of light, 1 year on the rocket, more than 70 years on Earth. This is the famous twin paradox, though I should tell you, it is not really a paradox at all. It is only paradoxical if you cling to the idea that time must be the same for everyone. Once you let go of that, it is just a consequence of the physics. Put one twin on a fast rocket, leave the other on Earth. Itov, the traveling twin, goes out into space, turns around, comes home. When she steps off the rocket, she is younger than her twin, genuinely, physically, biologically younger. Her cells have divided fewer times, her heart has beaten fewer times, fewer chemical reactions have unfolded in her body, her hair has grown less, she has aged less, she has traveled into the future. You might object, you might say, she did not really travel through time, she just experienced it more slowly. But think about what you are saying. She left Earth when both twins were 30. She spent what felt like 2 years on the rocket. She came home and her twin sister is 60. She has arrived in a world 30 years into her twin's future. She skipped decades. People she knew have grown old. Buildings have gone up. History has happened. And she missed all of it, not because she was asleep, but because time itself moved differently for her. That is what traveling to the future means. The only thing preventing us from doing this right now is engineering. The energy required to push a spacecraft to 99% of light speed is enormous, far beyond anything we can currently produce. But no law of physics forbids it. The equations do not say impossible, they say difficult. And nature is already doing it, right above your head, right now, at this very moment. Cosmic rays, high-energy protons hurled across the universe by exploding stars and violent galactic events slam into the upper atmosphere and produce showers of secondary particles, including muons. A muon is an unstable particle, a heavier cousin of the electron. It has a half-life of about 2.2 microseconds. That means in 2.2 millionths of a second, half of any group of muons will have decayed. Given their speed, close to the speed of light, they should only be able to travel about 600 meters before they disintegrate. They are born high in the atmosphere, roughly 15 kilometers up. By all rights, they should never reach the ground. The math says they should die long before they get here. But they do reach the ground. Muon detectors at sea level pick them up in enormous numbers, far more than should be possible if their clocks ticked at the same rate as ours. Time dilation stretches their brief lives. From our perspective, the muons live longer because their internal clocks run slow. From the muon's own perspective, the distance to the ground is shorter because lengths contract at high speeds. Either way you analyze it, relativity is what makes their impossible journey possible. Nature has been doing time travel with subatomic particles for billions of years, since long before anyone was around to argue about whether it counts. So forward time travel is real, confirmed, measured, engineered around, done. It is not a hypothesis, it is not speculative. It is as well established as the fact that the Earth goes around the Sun. But what about the other direction? Can you go backward in time? I want to be careful here because this is where solid physics shades into honest uncertainty, and I believe honest uncertainty is far more interesting than confident speculation. General relativity, Einstein's own magnificent theory, does allow certain mathematical solutions where time curves back on itself. These are called closed time-like curves, a path through space-time that loops around and returns to its own starting point so that you arrive back at the event you started from. In 1949, the brilliant logician Kurt Gödel, Einstein's friend and colleague at Princeton, found a solution to the field equations describing a rotating universe in which such loops exist. You could in principle travel along a path through this rotating cosmos and end up in your own past. Other physicists have explored wormholes, hypothetical tunnels connecting distant points in space-time, and found that under very specific, very exotic conditions, they might connect different times as well as different places. Frank Tipler proposed an infinitely long rotating cylinder. Kip Thorne explored traversable wormholes propped open with exotic matter. But every one of these solutions comes loaded with caveats. The size of galaxies. Gödel's universe requires the entire cosmos to be rotating in a specific way, and as far as we can tell, ours is not. Wormholes would require exotic matter with negative energy density to keep them open, and nobody has ever observed such a thing in bulk. Tipler's cylinder must be infinitely long, which is somewhat impractical. The energies involved in any of these schemes would be staggering beyond comprehension. And then there are the logical problems. If you can go back in time, you can change things. And if you can change things, you get paradoxes. You go back and prevent your own parents from meeting. Then you are never born. Then you never go back, so your parents do meet. So you are born. And round it goes. Physics does not like contradictions. Nature does not tolerate outcomes that are logically impossible. So either backward time travel truly is impossible, or there is some deep mechanism that prevents paradoxes from occurring. Some physicists have proposed self-consistency principles where you can visit the past but only in ways that are consistent with what already happened. You cannot change history because you were always part of it. Others, including Stephen Hawking, have suggested something he called the chronology protection conjecture, that the laws of physics somehow conspire to prevent anyone from ever building a time machine to the past. Every time you try, quantum effects or energy blow-ups at the threshold shut the project down, like a cosmic security system guarding the past from trespassers. The honest answer is this: we do not know. General relativity says maybe, under fantastically exotic conditions. Quantum mechanics whispers probably not, and we do not yet have a complete theory of quantum gravity, one that merges both frameworks, that could settle the question once and for all. Backward time travel remains genuinely open, not confirmed, not ruled out, but open. The forward direction, though, that is finished, that is done. That is measured to extraordinary precision. You are doing it right now, and you cannot opt out. So what should you carry away from all this? First, that time is not what your gut tells you. It is not a river flowing at a constant rate, indifferent to the world around it. It is something much more interesting. It is a dimension that stretches and compresses, that warps around massive objects, that dilates for fast-moving things. Different observers in different situations genuinely experience different amounts of time between the same two events, and neither one is wrong. Both are correct. The universe does not have a master clock ticking away somewhere. There is no universal now. Second, that forward time travel is not a matter of physics anymore. It is a matter of engineering. The physics says yes. Get moving fast enough, or park yourself next to a sufficiently massive object, and you will skip into the future. The question is not can we do it, but will we ever build the machines to do it dramatically? And third, something I find deeply beautiful. The flexibility of time is not a defect in reality. It is the architecture itself. The bending of time is inseparable from the existence of gravity, and gravity is what holds galaxies together, what collapses hydrogen into stars, what keeps the ground beneath your feet. If time did not bend, the universe as you know it, with its stars and planets and oceans and creatures asking questions about time, could not exist. Every particle in your body is a clock, and every one of those clocks is ticking at a rate determined by precisely where you are and exactly how fast you are moving through space. You are not just a passenger riding through time, you are woven from it. So the next time someone tells you time travel is impossible, you can tell them they are already doing it. Every airplane passenger who lands with a clock that subtly disagrees with the one on the ground, every satellite silently correcting its time so your map does not send you into a lake, every muon screaming through the atmosphere outliving its own expiration date because the universe is far more generous with time than Newton ever imagined. If you could board a ship, accelerate to 99% of the speed of light, and set a course for anywhere in the cosmos, knowing that centuries would pass on Earth while only years passed for you, where would you go and what would you hope to find when you came back?